Hello, welcome to Piercing the Air Gap Network Steganography for Everyone. I am John Ventura. I am part of the applied research team at Optiv, and I want to talk to you today about using steganographic techniques to hide data within network-based communications. As part of the research for this talk, I developed a tool. The tool is called NetNeedle, and it provides a network-based steganographic channel of communication between two hosts. You can use it for a variety of things depending on what you want to communicate across that channel. And there were a lot of lessons learned in that development, and I'd like to share those with you. Before we get to that, I'd like to talk about, maybe give you a brief history of steganography and the tools and techniques that have come before me. Before I do that, though, steganography, in case anybody doesn't know, this is the craft of creating hidden messages. In this case, we are hiding those messages within network protocols. Specifically, we are hiding those messages in the packet headers. Other people have done a lot of similar work in the past, and the first tool that comes to mind in that vein is Project Loki, where they took ICMP ping messages, echo requests, echo replies, and hid their actual messages within the payload. That approach is great. However, that payload sort of sticks out if you want to do analysis. If you want to find that channel of communication, the payload, the data that's being transmitted, looks pretty odd. Other people, when they want to use steganography in a network-based way, typically they use DNS tunneling. This is probably the most common at the moment way to do it, where they try to resolve a lot of crazy DNS names, and there were advantages to that, but we didn't go that route, partially because that data is, again, hidden in the payload, and if your network analyst wants to do some protocol analysis, again, that might stand out. Because this is steganography, we are trying to make our communications as discrete as possible. So again, we decided to use the packet headers. The payloads are used for decoy data. So in ICMP mode, it just looks like ping. In TCP mode, it looks like HTTP GET. And hopefully, network analysts who are going to try to find your communication channel, hopefully they'll be fooled. So there are some benefits here, and is anyone here a pen tester? All right. So if you're a pen tester, you can use these techniques. You can use the tool that we developed, or maybe even develop your own, and it will help you avoid detection. So if you don't want to be detected, if you want to communicate in such a way that whoever is responsible for monitoring network traffic doesn't see you, this will help you. If you assume that adversary exists, the person who's actually responsible and is monitoring network traffic, you can imagine software that they're using. They probably aren't just doing TCP dump and Notepad and trying to piece together all of this data manually. There is probably some sort of automated process, an IDS or an IPS or even Wireshark that interprets these protocols for them. Part of the advantage of what we're doing is that we are making it more computationally intensive to find you. So if, for example, if they want to if you hide your data in pseudo-random fields, pseudo-random data and cryptographic data look really similar, and this technique will require a lot more computational resources, and maybe they don't have those resources, or maybe they will spend that resources and they'll miss a lot of other things. So you are making yourself more difficult to find in maybe even some unexpected ways. And finally, a really useful application of this technology, if you're a pen tester, would be the establishment of a control channel in an environment where network filtering is restrictive. So if you can imagine a network where the admin has done network filtering in a responsible way. And by that, I mean they have an access list that actually does apply to the principle of least privilege. So, for example, if there is a web server within that network, the access list will only allow incoming traffic to TCP port 80 or TCP port 443 if they're using SSL, which hopefully they are. Now, in the past, if you wanted to set up a listener, if you wanted to establish a communication channel, this was a little complicated because the only way you could talk to that server was through that access list, through that restrictive firewall or whatever they have blocking those ports. And if they didn't have a hole in that, you couldn't listen on a service that was being used for something. Fortunately, these steganographic techniques allow you to do that. And let me be clear about this. You really can set up a listener on a port that's in use for something else, and hopefully that doesn't even get noticed. So if you're using TCP mode, by default, you will communicate on port 80 over HTTP. Apache will respond to that HTTP GET that you're sending, and hopefully the server that you set up will deconstruct and handle your datagrams appropriately. So in case you want to set up a difficult to find communication channel, there's definitely some benefits there. So when we talk about using the out-of-band headers for data transmission, specifically, I am talking about IP headers, TCP headers, UDP headers, ICMP headers. There is a lot of data within those headers that is random or arbitrary, and you can shove your data in there, and it works. I've done it. It's real. If you're choosing what fields you want to hide your data in, there are some precautions you should take. Obviously, you want your resulting data traffic to seem natural. You don't want it to look weird. If it looks weird, that obviously gives people a way to detect you. So, sort of like Chewbacca, fly casual. So in the past, people have done this sort of thing. There are some common areas that have been used before. What we used the IP ID field, which is a 16-byte field within the IP header, and there are some precautions there. It's not as simple as it sounds, but it gives you some flexibility. It's a pseudo-random field, so you can put whatever you want in there, and your traffic will still go through. Other people who have done this, and there's a doctoral thesis out there if you want to Google for it, have used RSTs. So they establish a legitimate TCP connection between point A and point B, and within that TCP connection, they send a lot of resets. So they reset the sequence numbers, and those new sequence numbers have the data stuffed into it. That can give you up to 8 bytes of throughput per packet, which for what we're doing is actually pretty good throughput. In practice, I don't think RSTs are all that common, so maybe it's not ideal, but unfortunately, none of these protocols were designed for these purposes, so I don't really know if ideal exists, but it's definitely a workable way. Also, in terms of sequence numbers for TCP, you can, and people have done this, you can send a bunch of SYNs, a bunch of connection requests from one end to the other, and again, you can have 4 or 8, depending on how you're doing it, packets per bytes per packet if you want to do it that way. Another way that's pretty common is to use source ports. So again, you fire off a bunch of datagrams and you get 2 bytes nearly per packet, and it's a little noisy, but it works. So if you're going to choose what fields to use, and again, we're talking about lessons learned in the design of one of these communication channels. There are some great fields, there are some horrible fields, and there are some fields that definitely come with some precautions. And I'd like to go over that now. In IPv4, and we really didn't touch on IPv6, so if there are IPv6 enthusiasts out there, and I'm with you, sorry, perhaps in the next version of this talk. So we took these diagrams from the RFCs. You can see RFC 791, which maybe you're familiar with, defines IPv4, and we have the 20 bytes here. The black fields, and let's start with version, you don't want to modify that. You don't want to modify type of service. If you do that, I really don't think your packets are going to get routed. If you change the version, yeah, I don't think the routers are going to know how to handle it. Maybe they will, but good luck. The red fields, and let's start with total length. Another way, and I didn't cover this in the previous slide, you could vary the length of your datagrams and hide the data that way. Again, that's not entirely, you're not really flying casual if you do that, but it would work. You can, what's that, a pointer? Header checksums are another place to go there, and the problem with header checksums is that some networking equipment won't necessarily route your traffic if you do that. You are also, an advantage here is that you are costing your adversary, the person monitoring you are costing them computational overhead because you are forcing them to calculate that checksum for each and every packet in order to find your broken checksums. It's difficult. Time to live is an interesting place. If you do a lot of network sniffing, you will not commonly see the TTL in a packet jump. However, it happens. It actually can happen within a data stream. You'll see that, and you can have you do have a little bit of space to bury data in there. And finally, what we chose to do was to use the IP identification field. And you can see part of the IP ID field is in the red, and part of it's in the green. If you are using Microsoft Windows, those red bits are zeros. If you are using Linux or BSD or most other operating systems, the whole field is used. We use the lower 8 bits of the field to hide our data because every OS uses it. If you should decide to pretend to be Windows, you can null out those red bits there and still seem natural. A caveat there, a really important thing to know if you are going to use the IP ID field, is that, and this caused a lot of headaches, it can't be 0. There's actually an RFC about that. Apparently IPsec breaks if it's 0, and if you try to do packet spoofing on Linux and you set your IP ID field to 0, Linux will fix that for you. Yeah. Which also, by the way, if anybody's ever tried to do packet spoofing from Windows, Windows does a lot of that kind of fixing for you. Yeah, these techniques are, they don't do Windows very well. Okay, TCP, again, we talked about the source ports and the sequence numbers. There are some reserved fields for within all of these protocols. The reserved fields I would kind of caution against. On the one hand, sure, they're reserved, and who are they reserved for? They're reserved for everybody, okay, for all of us. But typically they're 0, so you're kind of creating a signature for people if you're using them. Similarly, the window, it shouldn't have that much variability, but there's going to be some. The padding is just like the reserved fields in that typically it's going to be 0, but if you want to defy expectations there, maybe they won't see it. And again, the checksums, again, maybe some networking equipment is going to give you some problems if you have a broken checksum. Maybe some operating systems might even try to fix that checksum for you. But again, it is computationally intensive-ish, especially if you are monitoring thousands or tens of thousands or a whole country. UDP has similar issues. Again, the length field, we talked about modifying the length of the datagrams, and you absolutely can hide data there. The source address, which this is really strange because I copied that chart from the RFC. It says source address, but I think all of us would probably more commonly refer to it as a source port. But again, if you want to fire off a bunch of datagrams between point A and point B and change those source ports, it would be difficult to detect. And finally, ICMP. And the tool that we developed does have an ICMP mode as well as a TCP mode. In both of those modes, however, we are choosing the IP headers to hide our data. If you want to go a different route, you have some variability within ICMP. And specifically, again, the checksum is there. There are ICMP, it's assumed that the packets are going to be in a sequence. So you've got some sequence numbers there. If the packets arrive out of sequence, that feels a little detectable to me. But Again, it's a new signature, something that they would have to check for. And I'd like to talk a little bit about the data fields with an ICMP, because ICMP isn't just about echo requests. It's not just about ping. It's bigger than that. And you can do timestamps. Although we talked about not putting that data in the payload section, I think it's a little bit arguable in terms of where that payload section stops and starts with an ICMP. So if you are going to do timestamp requests, there are microseconds within that timestamp field, and I have serious doubts as to whether anyone really does have the computational wherewithal to check that field to check your microseconds. I think that would be really hard. Mind you, I haven't done the research on that. If timestamps follow really great predictable patterns without variability, that would be interesting to find out, but I kind of doubt it. There are also fields that are marked within, there are ICMP fields in some of the ICMP protocols that are marked as unused. And specifically, those include fields within the time exceeded and destination unreachable ICMP messages. Though, again, they're unused, so typically unused fields are 0, but maybe we can use them. And in the development of the tool that we created for this talk, we faced some problems, and there were solutions to those problems. And I want to present a theoretical framework for how you can develop your own network-based steganographic solutions, and maybe you won't hit your head against that wall as much as I did. And here's an anatomy of a steganographic system. If you follow this pattern, I think you can devise a workable solution for yourself, and you'll avoid some of the problems I did not get to avoid. So specifically, let's talk about the initiator. You have two nodes for this data channel. You have the sender and the receiver, and if it's two-way communication, the sender and the receiver will reverse depending on which way we're going. The initiator simply tells the other end when the data communication has started. So I think you really ought to choose something that happens naturally. And in ICMP mode, the choice that we made was an ICMP echo request packet whose sequence number was 1. And if you use Mac OS or Linux, if you use Linux, then the initial sequence number is 1. If you use Mac OS or most of the BSDs, the sequence number is going to be 0. The payload fields are roughly equivalent. I'm not really sure that difference there. Interestingly enough, the initial sequence number for Windows, that actually saves state between pings. So if you send 5 packets, your first time it's going to go 0 through 4. And then the next time you ping somebody, your initial sequence number is going to be 5. I don't know where that data gets stored, and I thought that was kind of an interesting anomaly there. You can choose a different sequence number if you want to start from 0, if you want to start from 87. But either way, I really recommend you use an initiator that is prone to false positives. That way, you are more difficult to detect. So the initiator that we use for TCP mode is a simple TCP SYN. The receiver, every time it sees a TCP SYN with a known destination address, it decides that it is going to reconstruct that datagram, and it's wrong a lot. But that's okay, because, again, that makes you more difficult to detect if that initiator event happens over and over again. You will also need a sequencer. So if you are designing any kind of a network protocol, anything that ever transmits data from point A to point B, you should not assume that your data will get from point A to point B in order. So you need something that has predictable numbers that either are sequentially naturally, or they follow a sequence that you control or can predict. And again, for TCP mode, we actually use the same sequence numbers that we all know and love for TCP. And for ICMP mode, again, it's the sequence number, because if you do ping somebody, those sequence numbers are going to increment by 1 each and every time. There's also, the next part of it is data receipt verification. And in short, the question you're answering there is, how do we know that our data actually got through? Now, The reason that I even bring this up at all is because once you lose that layer 4 of the protocol, man, you get a lot of problems. TCP does a lot of really nice work for you. And unfortunately, if you're doing a steganographic system, you've given all that up, and you really do have to reinvent the wheel a bit. And in both these cases, the solutions that we chose more or less piggybacked on what was already there. So the data receipt verification for ICMP was a simple echo response. Once we get that echo response, we know that the data that we just sent was received successfully, and we use the ACKs within a TCP data stream as acknowledgement packets. They're actually doing what they're supposed to do, but not necessarily in the way that their designers intended. There are probably other ways to do it, and if somebody wants to do that research, I would love to see it. And the final problem that we've identified that that anybody else who tries to come up with their own steganographic system will have to solve is termination and reassembly. How does the receiver of that datagram know that the datagram is complete? How does he know that he has all the data? Well, we took actually a streaming cipher and we turned it into a block cipher. So we count in both modes. We count the data packets. Once we get a full block, which by default is 256 bytes, we know to start decrypting that. You can send padding bytes after that if you want to obscure yourself a little bit more, but right now I just do byte counting. So an important thing to keep in mind here is that like all data transmissions, you really ought to use cryptography. And unfortunately, you do have a few concerns here that normally you will not encounter. If you're doing a new communication system and you want to use cryptography within that communication system, you would be well advised to use something like OpenSSL, something that exists, something that's a little bit more proven than anything you're likely to design. Unfortunately, what we're doing network-wise is a little weird, and SSL does not necessarily support that. And what we chose to use instead was and I'll give this a shout out because it's pretty good technology. We used a CryptoBox, which initially was a project started by Dan Bernstein, and it takes care of a lot of these problems for you. So again, cryptography is a good thing. It's helpful. We all know it. We all love it. But for a steganographic system, it also provides an added benefit in that it makes your data look random. So if you are hiding in a field like the IP-ID field or within TCP sequence numbers, if you're hiding in a field that is already populated by pseudo-random data, then you want your data to look as pseudo-random as possible. So if you encrypt it, chances are your data is going to look pretty random. Maybe it looks super random, maybe it just looks random, but if your adversary has to tell the difference, that's not computationally nothing. That actually takes some effort. And if there's a crypto guy in the audience, if you're great at that or if you're great at statistics, feel free to call me out on this. But I think you need about, for the system that we have, you need about 1,800 packets, give or take, before you can do that with any kind of reliability. And even then, you're still going to make some mistakes. So again, cryptography, in addition to all its conventional benefits, if you want your data to look random, it's definitely something to use. Now, there are other cryptographic concerns that you should keep in mind. Specifically, any kind of system that you use, you should really include a nonce. The reason for that is if you don't, then your datagrams are going to be repetitive. Your sequence numbers, your IP-ID fields, all the data that before maybe would have looked pseudo-random is going to repeat over and over again. And not only is that detectable, but if someone does detect you, he or she will be able to do a replay attack and take control of whatever nice server you fought to gain control of. They're just going to take it from you. In addition to that, I think public key cryptography is pretty crucial here. With any kind of cryptographic system, you need some kind of symmetric or asymmetric secrets on both sides, and you either need some kind of pre-shared key or something, and your choices, I would imagine if and there are probably, if someone's a crypto guy, there might even be better ideas than this, but the big choices that you have here are either a predefined public key, private key system, or Diffie-Hellman. And we didn't go with Diffie-Hellman for two reasons. The first of which is Diffie-Hellman is often by itself susceptible to man-in-the-middle attacks. If someone wants to pretend to be one of your end nodes and they want to do the Diffie-Hellman handshake, there's not really a lot stopping them. The public key, private key system, if you share that information initially, then you don't have that problem as much. You do have some cryptographic verification on both sides, and it also allows you to do asymmetric communications. So, and here's a good trick if you want to use a system like this. In ICMP mode, if you use packet spoofing and you change your source address to be the address of the machine with which you are communicating, then you can bounce those datagrams off of a third party and make it look like those datagrams are coming off that third party. So basically you make it look like the machine that you're communicating with is pinging that third party, and the third party does what it's supposed to do, and it responds with echo responses, which will be interpreted as data. So it will make you even harder to detect because they won't know for sure where you're coming from, especially if you change that reflector periodically. And I say this because I know there's some pen testers in the audience, and avoiding detection it's a big deal on a lot of pen tests. So here's a new technique. Go ahead. Also, data validation is an important feature, and CryptoBox again takes care of that for you. The first 16 bytes that you will send are actually going to be a digital signature. And if you don't do data validation, some joker is going to zor your traffic, and yeah, you're not going to like the results. So if you want to see this tool, it's available on GitHub, and you can see the URL there. And it is currently a Linux tool. If you want to port it to BSD or Mac OS, that's actually not that difficult. In contrast, the Windows port is extraordinarily difficult. If anybody's trying to do packet spoofing on Windows, that's really hard. And a lot of people are going to tell you to use libpcap. However, one of the design goals for this whole project was to not require the addition of any new drivers or kernel modules for either node. The way that we have it right now, you can do a static build and then just upload your binary. I think kernel modules or drivers, additional ones, are relatively easy to detect. So that was something that we wanted to avoid. And I made a promise to acknowledge Noah Badome here, because the whole project started with a late night conversation with Noah where we talked about data exfiltration and control channels. And so thanks, Noah. If anybody wants to see the tool in action, I've got a demo set up right now. So if there's interest, let's do it. All right, there's interest. Is that visible to everyone? All right, so the program itself is, I like to call it a servant, and I took that term from the P2P community, where it's a sort of a concatenation of server and client. So it is the same binary that does both ends. I tend to still think in terms of client-server, so what you're looking at right here is going to be the client end. So if you are controlling another machine, this is what you'll be doing. Let's actually... The commands are scriptable. You can write a script that does things automatically. So if you have a function that you want to do and you want to do it regularly and not get detected, it does help with that. Some of those commands include, you can see get and put. So just like with HTTP, the get and put commands will allow you to upload and download files from the other machine. There's an exec command, which allows you to do remote command execution. And if you have a two-way communication, you can see the output, and we'll see that shortly. There is a chat client. So if you don't want to do command and control, if you just want to talk to your buddy and have nobody have any idea that you're actually chatting, We provide you with a way to do that. I will give you a warning, however, in that if you happen to live in an oppressive regime and if you're a dissident, good for you, keep it up. But this technology is pretty untested, so don't risk your life on it yet. But it's there if you want to be the test case. So here are the commands that we're going to run on the client side just to set up communication. And again, we are using public key cryptography. So you can see there is a public key and a private key and a client key. The client key is simply the other side's public key. And the connect command defines the IP address for the other node that you're talking to. The other node doesn't need an IP address. Only the client needs it, unless you're doing chat, in which case you're both the client. All right. And here's the client end. And you can see this command, it looks a little bit crazy, but it's this way for a reason. And you don't have to do it this way. Again, the commands are scriptable. But I like this feature, so I'm gonna show it right now. The first third of this big blob here is the local public key, and then we have the local private key, and then finally the other end, the client's public key. It's all defined there in one big blob, and right there, it's running in the background. And all right, you can see in the process list, the key that we just had in the command line does not show up in the process list. If you do this in the real world, I'd strongly recommend that you get rid of your command history at this point. But assuming that you do that, if your client or adversarial regime or someone finds your control channel, they will have to pick that out of process memory. As soon as they shut that machine off or terminate your process, that whole task of recovering those keys becomes a lot more difficult. So nobody asked for that feature, but there it is. All right. So I'm going to execute a command just to show us doing it. And we did a simple ls. You can see the contents of the directory that we used for the build. We can do pretty much any command you want. I did this on purpose, the exec command, so you don't have to mess with regular expressions. Everything that comes after that space is just, everything that comes after that initial space is taken literally. So a space is a space, a period is a period, a star is a star. To me, that's more usable, but other people, I don't know. Now, on the other end, I want to show off a little bit about the design and how we did it. Now, there's also a TCP mode, but I think you're going to get the point once I show you the ICMP mode. Some of the packets in this Wireshark capture are legitimate normal ICMP echo requests, and some of them are not. So I think it would be a little bit difficult to tell the difference without some more meaningful examination. And yeah, so difficult that it's actually, I made the demo and I forget which ones were which, but the ones at the end are the legitimate ping. And you can see the datagram here at the end with these nice 0, 1, 2, 3, 4, 5, 6, 7. Everything is real. The timestamps there, everything's there, and this is the legitimate ping. And let's show you some of the packets from our illegitimate ping. I'm gonna ask in the payload section, did anybody see any significant changes in the payload? No, because there are none. The GNU ping client, the one that is going to be installed on most Linux distributions or in most Mac OS, well, it's either installed on your machine or something that you have is derived from it. We copied that. Our code more or less matches that. And again, with TCP mode, if people reconstruct the datagram that you send with TCP, they are going to see they're going to see an HTTP GET, which is going to be RFC compliant. In fact, if you hit an Apache machine this way, that Apache machine is going to dump, it's going to dump slash on you. Index.html or whatever is that default document in slash. It's going to come back at you. and hopefully the listener does its job and responds accordingly. And that's what we have. So in this talk, not only do you have a new tool, so if you're a pen tester and you want to avoid detection or establish a command and control channel on a server that is already open, that's already listening, we give that to you. But what I think is possibly more valuable, and what I tried to present here, are the principles behind it. So if somebody wants to make something better, I've already done at least some of the theoretical work for you. So that is roughly it in terms of my presentation. Do we have questions, or someone want to yell at me, or? Yes, sir. Yes, sir. Okay, the answer is yes and no. So in practice, if you want to hide it completely from the process table, there's not really a good way to do that without jumping into kernel land, which was our goal. We had a design goal of not jumping into kernel land. I say that because there's a lot of smart people in the audience. If somebody knows how to do that purely in user land, let me know. Now, what you can do purely in user land, however, is change the content of those fields. So argument 0, 1, 2, 3, 4, however many arguments you have, those are, at least in Linux, those are fields that programmatically you can change. And what we did is we took argument 1 and argument 2, everything that came after the program itself, and we just spaced them out. We just replaced them with spaces. Honestly, I'd have to look in the code because it's possible that I just put the terminating null at the first byte. I'm sorry, I don't remember which I did, but either one of those would have worked. Unfortunately, if you want to extend those strings, it actually doesn't work out that well for you. There might be some people who are better programmers than me in the audience, and that's great. But what you could do, and we'll go back to that process list. You can see /needle as your first argument there. You can replace that with anything you want easily, as long as you use that many or fewer characters. So yeah, I mean, there are other options you can make to hide it better, but I honestly don't think you can easily just remove it completely from the process table without having some fun in the kernel. If you want to tell me how I can do it without messing with the kernel, then do it. Otherwise, are we okay? I'm going to move to. Yes. Yes, and you can actually, well, I mean, you can do that from the command line also if you want to, yeah, if you want to call your argv, your argv0, if you want to call it PS or SSHD or something, and that works too. There are simpler ways to do that, but yeah, I like that as a feature request. I like that idea. Gentleman in the plaid? Oh, wow. I don't have real data on that. If you want me to guess, I honestly don't think it's happening that much, for a couple of reasons. A lot of the hardcore cryptographers who look at this will note, and I would say correctly, that to some extent we are relying on obscurity here. The whole idea of steganography, however, is about obscurity. This is just another method to help you hide, you know? The hardcore cryptographers don't like it, probably maybe for other reasons as well, but ultimately I think a lot of people would prefer control channels that are where you've got a mathematical proof that this is absolutely undetectable. I don't think that proof exists, you know? So yeah, I mean, but again, I don't think undetectable exists. I think we just made it really difficult. But I mean, the same thing with PGP. PGP is not unbreakable. It's just pretty good. Yeah, and if I had achieved PGP level of unbreakable, I'd be so proud of myself. Yeah, but in terms of how often it's happening in the wild, I have not heard a lot of malware researchers tell me that they're seeing this. But if somebody's a malware guy in the audience right now, if somebody's seeing this in the wild, feel free to volunteer that right now. Shout at me. Otherwise, my guess is not that much. Maybe after this talk, maybe this will be normal in a year. Sir? Oh, I like that idea. Okay. I like that idea. Yeah, because like right now, if you do with a process list, it's going to look like we're forked from yeah, from the kernel or okay, that's a good feature request. Thank you. Oh, reforking ourselves from another process there. But also, if you think about it, if you figure out a way to upload this to in a real world scenario, uh, if you do this in a real world scenario, and somehow you got this, you got the process to run from say Apache or something, if you put it in like a CGI-bin directory, it probably would look that way, unless you did the -k, in which case it does this what I would call daemoning by itself, or daemoning, sorry. But yeah, I like that idea. Okay, anybody else? Well, all right. Thank you for coming to my talk. Thank you for letting me speak on this topic. Um, I am John Ventura, John A. Ventura at Twitter. So feel free to reach out to me, or otherwise, again, thanks.